Welcome back, Calculus 2 students, to our second video in which we introduce a separable differential equation. Unlike an algebraic equation, in which your goal is to solve for a variable, in a differential equation, you have not only variables, but functions of those variables and derivatives of those functions, hence the name differential equation. In our particular case, we're looking for a function y that's going to satisfy the condition that its derivative is 3 times the value of the function. And so when you're trying to solve a differential equation, you're trying to find a function that satisfies the requested constraints. We seek a non-trivial solution. It would be very easy to notice that if y is identically 0, a constant function that always outputs 0, the derivative would also be 0, and hence we have a nice solution here. But that's not very interesting. There are more interesting functions that satisfy this equation. How do we solve this equation? Y prime equals 3y. I'm going to start by dividing both sides by y. Now, even though we are assuming that y is not identically 0, it's not the 0 constant function, we still should note here that this will only work when y is not equal to 0, because perhaps there are, y is a function where it's sometimes 0 and sometimes not. So for y not equal to 0, we can do this. We are now going to integrate both sides with respect to the variable x. Recall that y is itself a function of x, and so x is our independent variable here. On the left-hand side, I can rewrite that as 1 over y prime dx, and the right-hand side, I can factor out a 3. So on the right, we have a very easy antiderivative. Don't forget the arbitrary constant, so here I have plus c. On the left, if you watch the previous video in which we reviewed substitution, that y prime dx is the same thing as dy. And so now I can regard the left-hand side as simply an integral with respect to y. So we have natural log, absolute value of y. Normally we would put a constant here as well, but if we have a constant on both sides, we can combine those to a single constant on the right-hand side. The language that is often used is that the c on the right will absorb any constant from the left. And so we are left with natural log absolute y equals 3x plus c. Now as we come back to the original equation for review for a moment, because we're not done here, let's revisit our prime notation and replace it with the Leibniz notation. An alternative way to envision this process and to get to this point right here, and I've left, there we go, dy dx equals 3y, is to divide both sides by y, but also multiply by the dx. Now, this is where we mathematicians are happily abusing notation in a way that we've told students never to do. Dy dx is not a fraction. And yet, as long as we've got the integral in there, the differentials, dx and dy, will make sense in this context. And you can see this side and the right-hand side as well. And so this is a way that it's typically written from here to here. Regardless, we're going to end up with natural log absolute y equals 3x plus c. Well, what do we do from there? We can raise both sides as a power of the natural exponential base e. And so we'll have e to the natural log absolute y equals e to the power 3x plus c. It's important to note that we did not write e to the 3x plus e to the c. The entire 3x plus c is the exponent. On the left, your exponential and your logarithm are inverse functions, so you have absolute y. On the right, we have exponent laws that allow us to separate the 3x and the c in this manner. Now, e to the c is still just a constant. The absolute y over here suggests that y could be the plus or the minus of this expression. So we have an e to the c, and we also have a plus or minus to deal with. What we're going to do is replace both of those with a new constant, p. And let's make a note here that p is that plus or minus e to the c. Now, is it plus? Is it minus? And what is the value of c? What is the value of p that results from that? These are questions that require an additional constraint called an initial value, and we'll address that in the next video. For now, let's keep in mind that regardless of the value of c, this part is never going to be 0. P is never going to be 0. And the exponential is a non-zero function in general. And so our earlier assumption that y is not equal to 0 turns out to be warranted. And every function that's going to satisfy this differential equation is going to be an exponential function of this form. So in the next video, we're going to address this plus or minus and this c with something called an initial value.